Okay, here the recording in progress. Okay, so we are here. I'm finished with 9.1. I'm going to start 9.2 today. So I'm a little bit ahead. And we are over here. Okay, so we only have two more sections, 9.2 and 9.3, leading up to the next exam. However, we are going to get started with some of chapter 10 before the exam, which is on the 15th. Okay, so a little bit ahead, which means we may finish early today. We may finish early several days, but we'll see how it goes. Okay, and you should have gotten an email reply back from me about the quiz. And if you did not, then email me, let me know. But it's basically a derivation of the formula for the circumference of a circle, which is 2 pi r. Again, about the methodology, you were supposed to do it similar to problem 2 in section 8.1. I mentioned that before. So if you did it some other way, I may not have given you full credit for it. Okay, so you were supposed to do it in a similar fashion. But again, hope you would realize what's happening, especially in Calc 2, is you get a chance to derive a lot of the formulas that you first learned, you know, in middle school perhaps, but you didn't know where they came from, right? So in 6th or 7th grade, you may have heard, oh, sphere, surface area, 4 pi r squared, volume, 4/3 pi r cubed. Okay, I know how to plug everything in, but where does that formula come from, right? Okay, and by techniques of calculus, we do that. So we've derived those formulas, and I earlier derived by doing a volume of revolution, we derived a formula for the volume of a cone, 1/3 pi r squared h. Okay, and now this quiz, you hopefully developed the formula for the circumference of a circle, which we of course know is 2 pi r. And so a lot of these nice formulas you get come about from calculus. Okay, so anyway, 9.2. So on direction fields and Euler's method. Okay, so we're going to focus first on direction fields. This really should be two sections. Direction fields is a separate topic than Euler's method, but they brought it all together. Okay, so direction field, sometimes called a slope field. Direction fields, slope fields, page 591. Okay, I'll just show you what we're up against. So on page 592, here is a slope field, figure 3. Figure 4 is a slope field. And they happen to draw a particular solution, a solution curve that goes to 0, 1. They put the point 0, 1, and you just look at the way these lines are and just kind of follow it. Say, okay, it looks like over here it's going this way, and over here it's curving like so. So here's a particular solution curve. Okay, this is a slope field. This is a very practical for lots of things like fluid flow. You could even imagine water flowing like so, or an electric field, flow of electrons, electric field, magnetic field, fluid flow, air flow, all of those kind of dynamic situations where at any particular point, okay, saying, okay, now we're curving that way, or now we're curving that way, or now we're going in a straight line, or whatever. Okay. And some more slope fields. That's what they look like. Figure 6. And it looks like they give a particular solution curve. So if you drop something at the origin, let's say, okay, and where could it have come from? Maybe over here, and where does it look like it's going? It's curving like so, okay? So it could be the path of water, flow of water, or electrons, or air, or whatever, okay? Here's a slope field, and they have several solution curves. So if I drop the particle right here, let's say, it looks like it go like that, it could have come this way. And if you're over here, maybe it's like that, and over here it's maybe like that, and so on, okay? And some more slope fields. Okay, looks like you have a constant function. So if I drop the particle right at, looks like y equals 5, it just goes in a straight line. And I guess here's a situation where it's like all roads lead to 5. So no matter where you go, it's almost like y equals 5 is a funnel. If I'm a little bit below, it looks like the lines are funneling toward y equals 5 like so. If I'm a little bit above, I'm funneling toward y equals 5. And if I'm already at y equals 5, it just stays at y equals 5. So limit as t approaches infinity of this current function looks like it's 5. It all funnels toward 5, so to speak. Okay. They have some solution curves here. They start at some point. Okay, so if this is fluid flow, water flow, I drop the leaf here maybe, it curves toward y equals 5. If I drop it here, it still curves toward y equals 5, or at 2, 0, it seems to flow toward y equals 5, right? So it's a funneling effect. No matter where I drop the particle, it funnels toward y equals 5 in the long run. Okay. So the first thing you're going to do is draw some solution curves, and hopefully you'll find that that's not too bad. Okay, then we have Euler's method. That's later on. I'll get to that maybe tomorrow or Wednesday. But first thing is look at some slope feuds, direction feuds. So that would be the first problems, 1 and 2. We might as well knock them both off. And then let's see, we have 7 through 14 all. So 7 and 8 involve directions. Okay, so I'll try to at least knock those off and see what is going on. All right, so on page 597, 9.2. And yeah, let me go ahead and show you the book for those of you who don't have the book and aren't getting it. Page 597. Let's see, problem 1, like so. Problem 2. Next page. Let's see, we didn't have to do those. So 7 through 14, I think we had to do. Maybe making your own these. And then let's see, what else do we have to do? 19 and 21 to 24. Okay, 19. Here's 19. And 21 to 24. Those involve Euler's method. Okay. So problem 1. A direction field for the differential equation y prime equals x cosine of pi y is shown. So here's a differential equation. This is a corresponding slope field. So how do you come up with that? It's basically any point in the xy plane you plug in and come up with y prime. I'll show you how to do that. In fact, you're actually going to make some of these. Okay, don't get scared. Looks like there's a lot. Yeah, you will only have to do 49 of these for the ones that I give you. Okay, why 49? 49 happens to be 7 times 7. And we're going to go from -3 to 3, -3, -2, -1, 0, 1, 2, 3. That's 7 and 7 the other way for a grand total of 49 for any one problem. Okay, but don't worry, I'll show you when I get to it. But however they came up with this differential equation has this slope field right now. Okay, so right now, all they're saying is sketch the graph of the solutions that satisfy the given initial conditions. So you given this slope field, okay, you have an initial condition. So drop the particle, as it were, wherever they have you. And then which way is the graph going? Where could it have come from? Okay, so what do you mean by that? Okay, it says y of 0. Okay. A lot of the problems, they start with y of 0. I mean, you start at 0. 0 often refers to time. Start at time t equals 0, but you don't have to. You could start at 1 or 2, but normally we start at 0. So y of 0 is 0. We start at the origin. Okay, so let me just go ahead and plot the origin. So I'm doing I right now. Again, the way the lines are going, it looks like we're getting close to 0.5. So I'll just kind of go like that. And where could it have come from? It looks like it's curving back, like so. So that's all you got to do for 1AI. Okay, you're right here. You're right here. Pretend this is fluid flow. If I drop a tiny little leaf in this flow of water, looks like it could go this way, or where could it have come from? This way, kind of going back in time, so to speak. That's all. Y of 0 equals 0.5. 0.5, well, it looks like it's just going to be a horizontal line. right? So 0.5, I'm just going to try to go like this. Do it without missing it too much. Okay. Y of 0 is 0.5, straight line. Okay, this is sometimes called an equilibrium solution. Equilibrium solution. Just a horizontal line. So if you have a solution where you just have a horizontal line, that's called an equilibrium solution. So here's an equilibrium solution. Here's an equilibrium solution. Okay. So y equals a constant. Y equals some constant. Like it looks like y equals 0.5, y equals 1.5. And the way the pattern is, I guess it's 2.5 and so on. Okay, y of 0 equals 1. So y of 0 is 1. That's right here. So if you look at the way the lines are going, it looks like it's dropping down here and it's dropping down here. Okay, so just kind of go like that. And there we go. And finally, y of 0 equals 1.6. Now, if they said 1.5, it looks like 1.5. I just get another horizontal line there. 1.6 is a little bit higher. So you look at the way the lines are going, it looks like it's going up here. And if I go backwards, it looks like it's going up there. So maybe I'll go like so, sort of parabolic. And that's it. That's all there is to it. So a direction field, drop a particle somewhere, this fluid flow, water flow, air flow, flow of electrons, okay? Quite useful in a lot of physical situations. Okay. Find all the equilibrium solutions. So equilibrium solutions, again, y equals a constant, 0.5, 1.5. So the way it looks like the next one would be 2.5, 3.5, and negative 0.5. So we're going to say y equals 0.5 plus an integer plus k, where k is an integer. Okay. Meaning 0.5 plus 0 plus 1 plus 2 plus 3 minus 1 minus 2 minus 3. That seems to be the case. And a quick double check. If I plug in 0.5 for y, that's like half. So cosine of pi over 2 is 0. If I plug in 1.5, that's 3 over 2. Cosine of 3 pi over 2 is 0. Okay, if I plug in negative 0.5, I'm taking the cosine of negative pi over 2. That's also 0. So trig seems to bear that out, that all the equilibrium solutions, meaning y equals a constant, are 0.5 plus some integer. Okay. So that's it. So you drop a particle somewhere, look at the way the lines are, which way is it going? Where could it have come from? Like so. Okay, number 2, pretty similar. So this is y prime equals tangent of 1/2 pi y. Sketch the graphs of the solutions and give the initial conditions, blah, blah, blah. And find the equilibrium solutions. Maybe let's look at equilibrium solutions first. Looks like I got, you can't really see it so well, but y equals 0, y equals 2, y equals 4. So it's basically the even numbers. All right, so I'll answer that first. Y equals about 2k, where k is an integer. So that's it at part B. Okay. So if k is 0, you're right here. If k is 1, you're at y equals 2. If k is 2, you're at y equals 4, and negative 1, negative 2, and so on. And let's see, just curiosity, if I plug in here, what? 0, tangent of 0 is 0. If I plug in 2, let's see, plug in 2, I'm taking a tangent of pi, which is 0. And if I plug in 4, tangent of 2 pi, which is 0, yeah, so it seems to be working. All right, now drop the particle at 0, 1. And looks like it's going to curve here, and it came from curving back. So it looks like it would go something like this. Right? Y of 0 equals 0.2. So 0, 0.2, well, that's a little bit lower. But it looks like it's still going to curve the same direction. It's going to stay outside of these. And by the way, these solutions never touch in theory. Okay? So when I draw this one, it curves around, has the same general shape, but it should never touch the other one. For a very good reason. If it ever touched the other one, then it would just follow the same path. But we know it does not follow the same path. So that's that. Okay, y of 0 equals 2. Y of 0 equals 2, and it looks like my thing is frozen again. So we can take a break while I try to fix this. But yeah, let me blab on this a little bit more in case I never get any farther. So I can't point anything out to you now, but you can still hear me. Y equals 2 is a solution to 2a I. Just draw a horizontal line of y equals 2. Y of 1 equals 3, that's our first instance where you don't drop the particle at x equals 0, but at x equals 1. But it still looks like it would curve over. Okay, so if you can see where the point 1, 3 is, okay, and I can't point it out because it's frozen now, but it would still kind of curve to the left as all the others would. Okay, so while we have that in mind, you can try to fix that, but let me try to take care of this. So this might take 5 minutes, or I may never be able to fix it today. Let's see how it goes. Start from scratch again. Okay, I think we're back in business, or maybe not. Yeah, okay, I think we're good. All right, so I did I and I. Y of 0 is 2. That is going to be a horizontal line. All right. So let me see if I can draw it without tapping my chain tool. Okay, whoops, it's a little bit crooked. Y of 0 equals 2. All right, yeah, and y of 1 equals 3. So the vast majority of the time, we start at 0 because quite often x-axis represents time. Time is 0, that's natural. But you could start at 1. So 1, 3 is somewhere like over here, right? And the way the lines are going, it's still going to curve back to the left, and it came from curving back also. That would just still kind of go like that. So that's really all there is to it. Okay, so that's 1 and 2. Okay, so that was that. Now, some more 7 through 14. I think 7 and 8 are the only other ones. Seven and 8. Use a direction field labeled 1 above to sketch the graph of the solutions that satisfy the given initial conditions. Okay, so number 1. All right, so we're looking at this one. Okay, y of 0 equals 1. 0, 1. Okay, so let's see the way it's going. It looks like it's curving like that, and it came from there, right? Okay, B, y of 0 is 2.5. Let's see, that's 3, that's 4, so 2.5 is sort of like here. And the way the lines are going seems to be curving down, right? Like that, and like that. And y of 0 equals 3.5. So 3.5 is up here. It's still going to curve down, right? But be careful when you have the same general shape, it should technically not touch the other graph. So even though it's still kind of be curving like so, make sure it doesn't touch the other one. In theory, they never intersect, because if it did, they would eventually become the same graph, which they don't. Okay, so that's basically it. Okay, pretty straightforward, I think. And then number 8 is the last of this type. Use the direction field labeled 3 above. Okay, so look at this one. To sketch the graph of the solutions that satisfy the given initial conditions. Okay, so let's see. It looks to me like you have an equilibrium solution at y equals 0. And if you're below, it's curving toward y equals 0. And if you're above, it's also curving toward, oh, I'm sorry, looks like it's y equals 2. My bad. Y equals 2 is the equilibrium solution. Right. So we're curving like so. Everything seems to be going toward y equals 2. Okay. So let's see. Y of 0 is 1. That would be right over here. The way the lines are going, curve toward that. Y of 0 is 2.5. Okay, let's see. That's 3, so 2.5 is maybe like that. And curving toward y equals 2 as a horizontal asymptote. You're just kind of following the lines along. So everywhere in the XY plane, it's telling you which direction to go, so to speak. Okay, in this flow, fluid flow, direction field. And then what? Y of 0 is 3.5. So 3.5 is maybe like there, and it's still curving in the same general direction. Right. So everything funnels toward y equals 2, sort of a funneling effect. Drop the particle here, or here, or here, it's all going to curve toward y equals 2. All right, that's basically it, folks, for how that works. So I've already done 1, 2, 7, and 8. Okay, now I'll introduce you to the next part, and then maybe I'll just show you one, and that's about it. Much longer is how do you come up with this thing now? And how do they draw this stuff? That's what we're going to do now. So 9 through 14, sketch a direction field for the differential equation, then use it to sketch 3 solution curves. Okay. Now, there's a lot of stuff here, a lot of these lines. So, man, I have to draw all these lines. It looks like there's 100 something of them. No, you only, quote unquote, have to do 49 of them. Okay. It really should cover the entire XY plane. There's infinitely many points, but we're only going to go from -3 to 3. Okay, and I'll show you how to do that right now with 1, and then maybe that's about all we're going to do today. Okay, so number 9, y prime equals a half y. Sketch a direction field, and then use it to sketch 3 solution curves. Okay, so it looks like, by the way, these differential equations, the left-hand side is just y prime, not y double prime, not y prime plus anything else, just y prime. And then the right-hand side is a function of x and y. There's stuff that has x and y in it. Okay, so you're going to plug in an x and a y and come up with a slope. Okay, so let me see if I can show you number 9. Maybe that's how we're going to do. Okay, so we will make slope fields or direction fields on -3, 3 cross -3, 3. This notation cross, okay, it doesn't mean multiply. It means this is for x, this is for y, and using lattice points. Okay, what is a lattice point? It's a point in the xy plane where x and y are both integers. Okay, I mean, loosely speaking, they're quote unquote nice points. Okay, I mean, we like integers. We don't like fractions and decimals and irrationals and stuff like that. So lattice point from -3 to 3 means -3, -2, -1, 0, 1, 2, and 3. No fractions, no pi, no e, no square root of 2 over 2, anything like that. Okay. So they're asking us for a slope field, y prime equals a half y. I'm only going to make you do 49 numbers. So from -3 to 3 and 3 to -3. So when you set it up for me, make it exactly like this. If you want to put this directly on the cheat sheet. So you're always going to make a table like this for me. X here, Y here, -3, -2, -1, 0, 1, 2, 3. -3, -2, -1, 0, 1, 2, 3. And by the way, it should be exactly like this. Don't put -3 on top. The reason why we're having it this way is that's the way it is on a number line, right? What we're doing is we're imagining this is the origin. If this is the origin, how does X go? Well, negative is this way and positive is this way, right? And for Y, positive is this way and negative is this way. So we do want 3 at the top for Y. Okay, so even though when you're writing, you have an inclination maybe to go -3, -2, -1, and so on, it has to go this way because that's the way it is on the XY plane. And this is the way it is in the XY plane also. Negatives on this side and positives on this side. So here are 49 spots. Okay, 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5, 6, 7, 49. Okay. And then at each point, the slope is equal to half y. Now this is fairly straightforward because it doesn't depend on x. There's no x here. Okay. Now the differential equation problems that we have later on do involve x and y, so that's much harder. But here, all you have to do is look at the y value and take half of it. So it doesn't matter what the x is, just take half of the y. So half of 3 is 3 halves. So I filled in this entire chart with a bunch of 3 halves. So in this case, it's pretty easy. Now, mind you, when you do it for me on a quiz or a test, you actually have to write this whole thing in. So, that'll take some time. Okay, everywhere along here, y is 2. So I don't really care about x. Y is 2. Half of 2 is 1. So 1, 1, 1, 1, 1, 1. Plug in 1. 1 times a half is a half. Half, 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 half. Plug in 0, 0, 0, 0. Plug in -1, negative a half, negative a half, negative a half, all the way through. Plug in -2, -1, -1, and all of these are -3 halves, all the way through. Okay, I've already pre-done it so I can save time rather than writing out loud. Here it is. Okay, so I think you can understand this concept when you do it on your own later for homework or quiz or exam. Now, how do I make this stuff? Okay, so I make my XY plane. I only need to go from -3 to 3. That doesn't mean the other points aren't there. There's, 4, 7 is up here, and -1,000,000, +1,000,000 is over here somewhere, and pi, e is somewhere. But I'm just going to have you do these 49. Okay. So I made little dots. I draw my XY plane from -3 to 3, and put a dot here, 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 and so on. Okay. And y prime means slope. So each of these represents a slope. Imagine taking these 49 numbers. It's 49, right? 7 by 7. It's almost like copy and paste. Copy this, paste directly onto the XY plane. So pretend this says 3 halves, 3 halves, 3 halves, 3 halves, 1, 1, 1, 1, 1, 1, 1, half, 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 0, 0, 0, 0, 0, negative half, negative half, -1, -1, -1, 3 over 2, all the way through. Okay. But instead of writing the number, I draw a tiny little stub that has that slope. Meaning whenever y is 0, the slope is 0. So I know you can't really see it because it's the same as the x-axis, but in red, there's a little horizontal stub right there. 0, 0, 0, 0, 0, 0, slope of 0. The next ones you should be familiar with are slopes of 1 and -1. Slope of 1 goes up at a 45-degree angle. Slope of -1 falls at a 45-degree angle. So whenever y is 2, slope is 1, 1, 1, 1, 1, 1. So go up at a 45-degree angle. At y equals -2, I go down at a 45-degree angle. The others have varying levels of steepness. Okay, So whenever y is 1, the slope is a half. Okay. So in my mind, I go 2 to the right and 1 up. Right. That's what slope of a half means. So if you're in algebra 1, if I'm at this point, right, you would go over 2, up 1. You would draw that entire line. Only now we're not drawing that entire line. I just draw a tiny little stub like that. And all of these have the same slope. We know parallel lines have the same slope. So I just try to draw something parallel to all of these. All of these represent a slope of a half. All of these have a slope of 3 halves. So in my mind, 3 halves. That's over 2, 1, 2, up, 1, 2, 3. I'm not actually drawing it, but I just imagine I'm eyeballing it. I'm aiming in that direction, right? Over 2, up, 1, 2, 3. Okay. So from here, I pretend I connect it straight over there, but just draw a tiny little stub. And all these others have the same slope of 3 over 2, which means I'll just draw them parallel. So once you have any slope, just copy with parallel line segment. So there it is. And negative a half. So I go over 2, down 1. So I aim from here to here. So if I'm in algebra 1, right, I would draw this entire line. But here, I just aim in that direction. So negative a half. And then I just make all these others parallel to this, since I already know they're negative a half. And I already did negative 1 and negative 3 halves. So mentally, I just think over 2, down 1, 2, 3. I know it's not even on my graph, but I just aim in that direction. Okay. So if you're generally in the direction I'll give it to you, it's not like I'm going to measure and say, oh, you don't have a quite slope of, negative 3 over 2. It looks like negative 3 over 2.1. I'm not going to do that. Okay. Just see if it's generally in this correct direction. And so like that, and so on. So it's getting steeper the farther away I get from the x-axis, right? So these are going up, 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 and these are going down, 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 down. So there we go. Then they told me to graph 3 solution curves, 3 fundamentally different solution curves. Okay. And it generally should be obvious. If you have an equilibrium solution, draw that. And then one above and one below. So if I pick something above, it looks like it's going to curve that way. All the slopes are positive. And if I pick something below, all the slopes are negative. So it looks like it's going to be curving down. So here are three fundamentally different solution curves for this particular problem. Okay. So go like that and go like that. All right. This one was fairly straightforward and easy, I think, just because the function y prime does not depend on x. Okay, the one I'll do next time depends on x and y, so there's more plugging in, but this was fairly straightforward, I hope. Okay. All right, folks, I was pretty much done for the day. So if you have any questions, you can bring them up. I am starting 9.2 already, so I'm a little bit ahead. Okay. And so quick look at the calendar. So this Friday, we have another quiz. Where are we? Over here. Next exam is on the 15th. Reminder, 13th, next week on Wednesday is a flex day. There's no CSM classes at all for October the 13th, it looks like. All right, I'm done, folks. Let me stop this share and check the chat. If not, we will adjourn for the day. Okay, any questions, please? All right, have a good day, everybody. That's it. See you next time. Okay, bye.
Thank you.
Thank you.